My name is Guevara Noubir from Northeastern University. This talk is about wireless and mobile security problems, and specifically the trend that we have that wireless systems are softwareized, and that drives many of the security. So I'll talk a little bit about an introduction, wireless, and even before that, the trends in cybersecurity. And then I will cover a variety of attacks in the wireless and mobile space, and then conclude with how we could be building future wireless and mobile systems that will be secure. And before I get into more wireless aspects, just looking back at how a system from a security perspective is designed. We typically have a model for the designer or developer or the attacker that makes some assumptions. Ideally, we have some proofs of and guarantees of security. And then an adversary, a smart adversary, looks into these these assumptions and escapes the model, meaning that there's no need for it to attack what's proven to be secure. It would try to evade it. And we have many examples, side channel attacks being the prime example. And once these kind of attacks are discovered, we solve them, we address these issues. And ideally for long term, and this control loop is quite pervasive in the space of security. So if you look at non-wireless and mobile data breaches, allowed us to see how secure we are, how well are we doing. And if you look a few years ago, about 10 years ago, there were few data breaches. And there are several reasons why, at least it looks like this. Then if you go a little bit after, you start having more and more massive data breaches. And if you look at the recent years, it's huge in terms of the size of these data breaches. Initially, it was in 10 millions, the 100 millions, now we are in the billion kind of entry data breaches. And one could look at a specific case of password leaks that allowed us to understand how many of these companies are doing in terms of applying best practices. So in this graph, we can see that, let's say, Adobe a few years ago was at the top in terms of the size of data breach. Over 150 million entries that leaked. And this is some information from analysis done quickly by Naked Security. And you see what leaked, from what leaked. We see, well, there's information about, there's a user ID, username, email address, and there is some kind of hash and some password hint. And from this analysis, you could see that, first of all, these hashes are not following the best practices. They're not salted. Why? Because if you look at here, these examples, these three of them get the same hash for the same kind of password. You can tell this from the hint. They're using most probably ECB mode. Why? Because if you look at this, all the same thing. So if you're using CBC, they would not. And they're not using AES because the length of them is 8 bytes, so you could infer that something like DES or triple DES. And this, despite the fact that for many years we've been teaching that to be able to protect passwords or even encrypt in general, you should not use ECB mode. Because if you were to encrypt the Linux Penguin, you'll get this, which leaks a lot of information. You should be using something like CBC mode. And in addition to this, we've known since the 70s that to really protect password against cracking, many of the basic techniques do not really work. And this is, say, DES crypt. I mean, many of these schemes cost, less than, about $1 in terms of, if you wanted to attack them. And over the years, developed better and better techniques. None of them were used in that case of Adobe. In the recent years, we have PBKDF2, bcrypt, scrypt that are much better, but none of them were used. Now this results in a paper that's 10 years old, and if you look in the recent years, there were things that were not really expected. For instance, cryptocurrencies changed a little bit things because some of the hashing functions were used for mining, and therefore people developed hardware that can do tens of tera hashes per second for a few $100s. This is an example where you could do script, which is known to be much more secure than what Adobe is using, but you could do 14 tera hashes, which is basically you could crack 40 bits entropy passwords in 1 second. And this is for a very reasonable cost. And one could say, well, maybe we have the technology and the companies will do better and so on. But it's not really true. A few months ago, it was revealed that Facebook was storing hundreds of millions of user passwords in plain text, and this for years. So it doesn't look like companies really improve their security unless if they're exposed. So what we can observe is that many of systems lag behind in terms of security in general. They underestimate attacks. There's an inertia. Systems are designed and deployed, but then it's very hard to change them. Security mechanisms are not user-friendly, and there are more and more attacks that span the foundations, the design, and the implementation of most systems. Now, when you add to this the fact that incentives are increasing because it's possible to monetize attacks, and we have also, or adversary has the possibility to hide. And for example, with things like Tor, attacks can come from almost anywhere, or with hidden services, attacker can do, for instance, ransomware, get paid in Bitcoins, and if he's using them correctly, not be discovered by, for instance, running its ransomware server behind Tor. So now you add to this connectivity, open source software and hardware, and bring your own devices. There are lots of security issues that are possible, and all of these issues are exacerbated in the context of wireless and mobile. Now, to go into the details a little bit more about wireless systems, wireless is ubiquitous. We know about it in cellular, Wi-Fi, and Bluetooth, but it's also GPS, not only for localization, but also in assisting air traffic, assisting in synchronizing the smart grid. Power plants use the GPS to get timing information, the timestamps measurements. Transportation systems, implantable devices, all of them have significant security and robustness issues. So it's important to really understand the security issues, but not only to strengthen security, but also wireless is used for adversarial attacks. For example, there's an example of right after World War II, Soviet Union gave a gift to the US embassy in Moscow, where it was this what's called the Great Seal bug. In fact, it was a passive device, does not need a battery, but if you send electromagnetic wave from the outside world, if someone is talking in the room where this device is there, the energy bounced back, or the wave as bounced back on the harmonics is modulated by the voice that's in the room, and they listen to what's happening in the room. Terrorists have been using wireless to trigger IEDs, and more recently, drones have been used for adversarial purposes. Now, in terms of secure wireless, one would have to understand the fundamental characteristics. It's a broadcast medium. Anybody can transmit and listen. The spectrum is limited and more scarce. Therefore, we design algorithms to optimize its use. Energy is also limited in these devices. If you open any device, you'll find that there used to be a battery that's this big, but then gradually the battery just gets bigger because the constraint is energy. Energy and spectrum limitations led to complex designs that make most of these wireless systems significantly vulnerable to attacks. So the assumptions in design of wireless mobile systems for security were that wireless systems are complex. Therefore, an attacker would not have the ability to reverse engineer and implement all these protocols and attack them. Attacks are impractical. Adversary has to be local. adversary needs to operate over a wide spectrum, and therefore it is not trivial. Adversary needs to operate in real time, for example, to jam, or then why would an adversary do this? What's the incentive? And finally, that if an adversary do this, it would be caught because it had to be locked. And many of these assumptions are not true anymore. Jamming used to require large devices. Today, on YouTube, one can find videos showing how a microwave oven can be repurposed to build a jammer, a 1 kilowatt jammer, by taking the magnetron, redesigning or repurposing it and changing the cavity that's in it for the resonance frequency so that it could jam on different frequencies. So also radios are becoming more and more popular, cheaper, and more powerful. If you take something like the XTRX, can operate over 100 megahertz of spectrum, up to more than 4 gigahertz. It has 2x2 antenna, GPS, and many other things. If you take Broadcom chipsets, they can be programmed, and recently people discovered bugs in them so that you can take over the Wi-Fi chipset. And finally, cyber mines and so on. So software in wireless is pervasive. Software libraries are pervasive, and therefore it is possible to do many attacks. The question is, if this is what we've seen in the context of, let's say, web security or system security, how would it look like in the context of wireless once all of these attack technologies come together? And this is not only of interest to military applications. Smart jamming allows an adversary to remove a 2G network, to a 3G or higher network, present a 2G network that has only one-way authentication, and intercept communication, inject traffic. Similarly, we showed that WP Enterprise has similar issues, and there are still many protocols that are not secure that rely on wireless. Public safety, P25, it's an adversary can intercept the communication, can listen on these devices. This is used by police and firefighters and so on. Aviation standards like ADS-B, that's a requirement 2020, has many security issues. The instrument landing system that helps aircraft land correctly, we showed recently that it has many security issues, and I'm going to mention these things very quickly soon. So starting a little bit more in details about attacks. If you take cellular system, let's say GSM, because it's simpler to explain, but these attacks apply also to more sophisticated systems. If you take such a system, it operates over many bands of 200 kilohertz. Very few of them, many times one, has most of the control traffic, and adversary jamming that single band blocks all communication. All the other bands are for data. And in fact, even if you look at that 200 kilohertz band, it's divided into 8 time slots from 0 to 7. And then the frames repeat themselves. These frames of 8 times repeat themselves, and very few of them have critical information. For example, here, this is broadcast control channel. If someone jams it, the network disappears. So an adversary can, by sending one pulse in 1 out of 10,000 or more time slots, can make a network disappear. These attacks also apply to LTE and many other systems. So it's fairly easy to make network disappear. Then an adversary might be able to, or would be able to present a 2G network if it jams 3G or 4G, can also track users, can insert SMS, tweets, and so on. So we've been warning about these things for many years. 2014, there was some instance of these being detected in the US, and 2 years ago, many of these fake base stations started emerging, and they're not even using the most sophisticated techniques. They start emerging mostly in China, but they could be anywhere. Jamming in most commercial systems is fairly easy. Typically, you have a number of bits that you encode, interleave, and modulate. If there is no interleaving and no coding, one pulse can destroy packet. packet that could be an IP packet, 12,000 bits. So the adversary will get 40 dB, or basically, a gain of 1 over 10,000. So communication nodes will have to spend 10,000 times more energy to defeat it. As you start putting coding, and even if you have interleaving, the adversary who knows how the interleaving happen can send jamming pulses at the right locations such that when they get de-interleaved, they create enough interference to destroy a packet. And we published these kind of things many years ago and recently showed that you can achieve these things against Wi-Fi systems. And this is an example of someone jamming only some of the subcarriers in spectrum and blocking all communication here at, let's say, 30 dB, which means that the communicating nodes have to spend 1,000 times more energy to defeat it. And with some additional techniques, you get almost to 40 dB, or with combined with other things, you get 5 orders of magnitude lower energy cost for the adversary. There are various other attacks an adversary can use. For instance, if a communicating node is jammed, it would typically reduce its rate to become more strong because it assumes that the link is not good. By doing this, an adversary might force one node to be transmitting at the lowest rate, 1 megabit per second, and therefore blocking other nodes. And we could show that maybe, or that this could lead to what we call a congestion collapse, where nodes on their own will start blocking each other if a certain phenomena is triggered. And this would remain for a long time. We showed also that adversary might be able to start some interference in one location that will propagate many hops away in the context of Wi-Fi. For example, here, node A0 is communicating with B0, and as it starts creating some form of interference here, all the other ones, node 20 and 40, performance drops. We show that in the context of Wi-Fi, an adversary who's able to efficiently jam, and here we could show that it is possible within 400 meters, can target a specific user based on its MAC address, and then disconnect it. So through, maybe just to explain how WP Enterprise, which is the most secure and common Wi-Fi authentication system, clients connect to a radio server over TLS connection. Now, if an adversary comes and jams existing connection, can trigger the client to connect to a rogue access point. And this by jamming the probe request of the client and sending probe responses that contain SSID, and using various other techniques can get it to connect. Now, the client assumes that because connected over TLS, it can use MS-CHAP v2, a less secure protocol being tunneled inside. But we show that, in fact, as long as an adversary has a valid certificate signed by some authority, you can get users to connect, and then you can conduct these attacks. And then more recently, researchers showed that as we design chips that have both the digital part and the radio together, it is possible that computation can leak to the radio and then show up in the spectrum. And you could show that if you're executing AES encryption, it was feasible for them within 10 meters to do a side channel attack or power analysis attack and infer what is the key that's being used in that AES encryption. As I mentioned earlier, cyber physical systems rely on wireless communication. The power grid, researchers showed that it can be desynchronized and can be tripped to generate cascading failures. Aviation systems like ADSB, where planes are broadcasting the location and speed, can be, so it's fairly easy for one to infer what's the location, but also to create ghost appearances of an airplane, possibly triggering issues with the aircraft systems. I think one of the most interesting things is that in a paper last year, researchers showed that by just looking at information broadcast by plane, and especially planes that belong to large corporations, they could predict mergers, acquisitions, but also in the context of planes belonging to states, relations between states, information that's not really public. In work that we did this year, we could show that, in fact, if you look at the instrument landing system used by airplanes, an adversary would be able to get a plane to land off the runway. And why? Is because the ILS system was designed many, many years ago, and it was designed such that most of the complexity is on the ground. The devices on the planes is fairly simple. And such that if a plane is not aligned with the runway, it would, by measuring two tones, it would be able to tell if it's too much to the right or to the left. And therefore, an adversary who either places a malicious device on the plane or outside can trigger this. The challenge was that to show that, in fact, this can be done in a way that the signal is adjusted dynamically, such that the pilot would not notice anything as it's landing off the runway. So tracking is another issue in wireless systems. And this is becoming easier and easier with softwareization. We recently analyzed Apple Wireless Direct Link, and we could show that it is, so this is Apple Wireless Direct Link is used by Apple to, in many of the devices, iOS, macOS, tvOS, watchOS, and so on. It's used for AirDrop, and it relies on two things, Bluetooth LE and Wi-Fi. And we could discover there are design and implementation issues in it. For instance, if you try to communicate with, let's say, your watch or your phone, the one device will be sending, or even you try to maybe use AirDrop to transfer some data. You broadcast a hash of somehow your identity into 16 bits. And now the other devices, if they see that one of their contacts has the same hash, they will wake up and send a Wi-Fi packet with some information for you to further communicate. 16 bits, that's 65,000 possibilities, fairly easy for someone to send them very quickly, and we could show that's feasible, and therefore get all the devices to wake up and respond. We could show that, in fact, then you can conduct additional attacks, for example, crashing devices in an area, either targeted or all of them. And more importantly, you could show that, in fact, you can disconnect two devices trying to do AirDrop and intercept what they're sending and replace the file. And I'm going to show just very quickly a video here that shows that you could do this with a $20 device like the microbit. So this is crashed, and the next attack, you're going to target all of them at the same time, and they're going to all be crashed. And so we informed Apple, and they fixed most of these, but the tracking attack is still not completely fixed. Tracking is not feasible at the higher layers. It's feasible also at the physical layer by analyzing unique characteristics of the radio interfaces. Adversary can also sniff LTE traffic, and by analyzing a variety of identifiers, can track users, can also look at how much traffic is being sent from a device, and can fingerprint it based on the list of applications that are installed on it, each one of them having a unique characteristic. So there is a need to revise the models about the adversary. Softwareization is making it feasible for an adversary to conduct attacks almost on any wireless system, Wi-Fi, Bluetooth, cellular, and so on. Most of these standards can be implemented and are available as open source software. Adversary can decode, encode, mimic any protocol, can operate over a wide spectrum and in real time, can sense and intercept RF emissions anywhere, even without being local, as shown by the Google Project Zero attack. Adversary might want to intercept or block communication. He might want to infer the location or the type of traffic, might want to deceive someone to get him to transmit and therefore use him as its own transmitter or its own jammer. And the adversary might want to intentionally or unintentionally jam, like in GPS case a few years ago, where a truck driver was placing a GPS jammer to not be tracked by its employer, ended up blocking New York airport for many months. Or adversary might put a fake base station. So therefore, we need to revise our models, knowing that softwareization is enabling flexibility, agility, and so on in terms of adversary, and therefore our system have to be flexible, agile, and robust, and security should be by design preventing against software attacks. For instance, trusted execution environment for RF, where an adversary cannot run the code even if it was able to compromise an RF interface. Unfortunately, today's wireless systems are not there yet. They're brittle, they have complex control mechanisms, they're prone to cross-layer attacks. Yet, wireless is becoming more and more ubiquitous in cyber and physical worlds. The attacks on the wireless link have implications on the whole system. And unfortunately, in the wireless world, vulnerabilities are not that easily fixed, and they take many years because the standards are fairly slow to move, unlike existing systems. So I was initially going to talk also a little bit more about mobile systems. I'm just going to go very quickly over this. A few years ago, we were looking into what kind of malicious app do. And we started by, we wanted to know what would a flashlight do even if it had no access to permissions. And then we discovered, in fact, most flashlight apps request many permissions. For instance, they want precise location, the access to photos, and they can access to camera and so on, while they only need to control the flashlight. In fact, there were lawsuits and some of these companies had to settle. But in fact, at the end, they only updated their privacy policy saying that they collect geolocation information and they share it with other entities. And that's how they make money. In fact, this app has 4.7 stars. Maybe apps that have less features, require less permissions, but have same feature, which is to turn the flash on, get lower ratings, in fact. So the question is, if an adversary managed to install an app and made the app look quite nice because, or in terms of privacy, because it does not have any permissions, what could it do? Now, most phones have many sensors: gyroscope, accelerometer, compass, microphone, cameras. And many of these do not require any permissions. So apps won't even mention that they're using these things. So what can adversary do? And we could show, in fact, that you could infer gender, age, and health information and so on, but you could also track users. You can find the location where they are, and you can even infer what someone is typing on its keyboard. For inferring location, if you just use the compass, as someone is moving from one location and following a path, the gyroscope provides information about these terms. And we could show that just from the gyroscope, it is feasible to infer these locations. So how is this done? If you take a city and you use, let's say, something like OpenStreetMap that gives you information about all the sections. And for each section, you create a vertex. And for each intersection, you create an edge and you label it with the angle. And now you have a graph, and based on the gyroscope information, the problem is, can we infer which path was taken on this graph based on the sequence of turns? And this problem could show that it can be solved, and the algorithm outputs the paths that might be taken by order of likelihood. And we could get to something, let's say 50% to find the right path in the top 10, And we did experiments in the Boston area, over 1,000 kilometers driven, and to confirm that this attack is feasible. Another attack, which is about inferring what someone is typing on the keyboard. So this is, if you think about it, when you tap on the keyboard, you turn, by pushing, you push your phone more to the left, or you rotate to the right, or top or bottom. If you tap in the middle, it doesn't really rotate and so on. So for instance, this is someone typing character Q twice, and the pattern is fairly simple, similar. If someone is tapping V, again, the pattern is similar. If now you add to it that if you tap on the phone, you make a sound, and most phones have 2 to 3 microphones. With just 2 microphones, we could show that it's possible to triangulate where someone is tapping. And we could show that with just a gyroscope, an adversary can get 60% accuracy in predicting what someone is typing, and 90% if it uses the microphone. Adversary does not have, in fact, to do this all the time. We can just find out which activity is in the foreground, and if it's a critical activity like a bank application, start the attack. Doesn't even need to have an app installed. He can maybe hack into an app that has access to a microphone. Recently, the WhatsApp was hacked because it has a vulnerability. Would show also that it's possible to exfiltrate information from an app that does not have permissions, and therefore a user would trust it maybe to put passwords and other things. And an app that has permissions, but where the user does not put any critical information. And one type of cover channel is by generating ultrasonic signals that cannot be heard, like these here, and measuring on the accelerometer that does not require permission. You can create this cover channel without requiring permissions. And it's in fact very interesting because you'll find that there are many channels that are possible there for each axis, and each device has its own channel and so on. So the question is the way of building security, the way we've been doing it, acceptable? Is this control loop stable, where you model and you react to these attacks? And here's my opinion is that, we have to change how we do things. We have to have better understanding of wireless systems. And there are many misconceptions. One would have to go back to the foundations. We have to make sure that the design is systematic, to have a clear model for the attacks, that also proactively modeling what could happen in the future, considering software-enabled attacks, building secure timing and localization, elastic networks, such that if an adversary puts more effort trying to attack system, it does not really break it. There's no exploit that can amplify weaknesses. And we've been designing systems like this with what we call elastic networks that cover from the physical layer to the application layer. So these are some of the illustrations of these systems where we could show that robustness is feasible in a smart way and adaptive. Context of systems, we also showed that we built this framework that we call matrix. It has 2 components. One is a private scope, and when you run it on your system, you'll get graphs that show you for each app which services it accessed, like which sensors, which location service and so on. It will give you that information. It will give you the historical data. It will allow apps that you'd allow to look into that data and infer malicious behavior. But it also allows you with matrix to sandbox an application and create synthetic information. For instance, you could create an identity where you say, well, I live in this location, I work at this location, I have 2 kids go to these schools, I like to eat in restaurants, or create a default identity for me and feed it to these apps. And you could decide, I want to provide precise information or less precise to these apps. So to start concluding, the fact is that wireless and mobile systems have vulnerabilities that are intrinsic to the constraints and the design choices that were made over the last few decades. But now, as hardware is being softwareized, in the sense that the whole wireless stack from the RF is in software, that wireless is pervasive, and mobile similarly, that there are resource constraints, and that we don't have systematic approaches for modern security and wireless and mobile. We need to change this. We should also realize that we only see the tip of the iceberg. Sophisticated adversaries can conduct powerful attacks. IoT would take these attacks to the next level because it's pervasive, it's wireless, it has sensors like microphones and cameras and so on. And we don't really know how it could be leveraged, as we would have tens of devices, IoT devices in our homes. And finally, attribution is getting harder because an adversary hiding behind the Tor onion services and cryptocurrencies can commit a crime and be paid for it without being identified. So what should we do, especially as wireless and mobile is in cyber physical systems, dynamic spectrum assets, 5G and IoT and so on? Can theory play a bigger role in making wireless communication systems and not having this reactive approach to fixing things? So there are some possibilities, especially as 5G is maturing and so on, but we have to be vigilant. And that's the end of my talk. Thank you very much for the invitation.